Hello, this is Christian Hübschle with a new tutorial on Shellixle, and today we want to solve and refine a structure which has a little bit of disorder. So we start just by solving the structure again with shellxt. So like this, and let's see, so as input solution A is PNMA, so we choose solution A like this, and we see, looks quite interesting, and here's something looking a bit strange. So first I get some automatic labeling for this structure, trying if that works. Seems to be the case. So 22 atoms out of 22 successfully renamed, and so we have two residues because we have two molecules here, and but here there is something strange going on. So let's see what it is. So we have here C number 12 fully occupied, and as we see here with 10.5 means half occupied, most of the atoms are on a special position, so it's on a mirror plane, and the same is for this BF4 anion, so where we have most of the atoms are in the plane, and just fluorine 1 here is out of the plane and has a symmetry equivalent over here. So so we want to add something, and probably we want to use a program called DSR for that. So we go into tools and try to start the DSR plugin, and it tells us we do not have installed that. So we just click here on this link, and we end up on this site here where we just can download this DSR for our operating system. In this case it's just Windows, and so we go to our download directory, and we just install this program. So we want to do that because we trust Daniel Krasset, who made this very useful program. So we just follow the installation instructions. Yes, like this, and so we close this thing now and try it again. Or probably we have to start our program also again, and probably we just choose already 3 atoms because that's necessary for that program, and we see now DSR has correctly started, and we have to figure out of the list here our part. So tetrafluoroborate, that's it, and we just do the same here. Here we don't need to use the control key to select several atoms. I just click them in a row, and we see there's an overlap now showing that our selected atoms and what this model is completely overlaps, so that's a perfect fit. And now we have to make some decisions. So this is on a special position, and therefore we use part -1. And yeah, so I guess this thing can use a free variable. So let's take free variable number 2, and we want to replace the target. And of course, yes, seems to be a good idea to use a residue here. So we just click now on fit fragment. Ta-da! Seems to have worked successfully. So we have here now a complete set tetrafluoroborate molecule, including the appropriate restraints for that molecule. So shouldn't happen anything strange anymore. So, and we use the free variable 2, indicated by this 21 over here, and this free variable 2 is initiated with 0.5, which I think could be a good idea in this case. So let's just try and refine to see what is happening, and we see let's focus that into the center. So we see that molecule is a bit disordered in this case, which is okay, because it's only half occupied, so it can rotate a bit. And we see that several atoms are quite near to each other, so F3 and F4 are very close, so probably it's a good idea to constrain the ADPs for atoms which are very close. So let's say those should share the same ADP. So these two atoms are already the same, and this is also the same. So I think that's it for the moment. And let's see what we can do here. It seems to be, I think, something like propene, or similar molecules. So we have something which has double bonds, because that's a bit short for single bond. So probably we look into the DSR database to have something like do we have such a thing? Seems not to be the case, so probably we have to do it in our own way. So that's okay. So we just used rename mode, and we use the residue 1 because this is all in residue 1, and we want to put that into a negative part as well. And probably we want to use a free variable. We could use the same one, or we can use a different one. Let's try a different one for that, and we just use the same labels. So this is starting with C12, C13. Okay, maybe we C12. So, and here deselect, so C12, C13, C14, like this. And we save the whole thing. So now we have this in that way, and probably we want to have a same distance command. So we say sadi C12 C13 is equal length then C13 C14, and this is residue 1, so we take the underscore here and say 1. Let's see what happens. Oh, that doesn't work. Yeah, we see that doesn't work, and so that's not a big issue. So we go just into the save history and just go one step back like this. So here everything seems to be in order, and it seems to be that we have to constrain not only that those have to have the same distance, we have to also fix the distance to those 3 atoms. So we add a restraint probably just like this first. So we add a restraint defix, and probably we use a bit smaller standard deviation like this, and let's see what it had added here like that. So we just add C13 C14 by hand, which is for me a bit easier at the moment. So let's see if it now stays in place. No, it's not. Let's see what else have we done wrongly. So it seems to be that we have here mixed occupancies, which doesn't make sense when we add this to a free variable. So so we go back again with the save history, and we just open that. So we have here our the defix thing isn't added here, right? So we add the defix for it has to be residue specific. So, and this time I will change all of that into 31. And where's the defix? So we need C13 C12 and probably keep it in that way in place. Let's see, it seems to have worked this time. Sorry for having problems. So one thing you have to see, learn, if you do disorder, there is not a straight way of doing it. It's always experimenting around and figuring out the right way of it. So one thing you could see, we still isotropic with our isotropic thermal parameters for each atoms, and this is very quick done. Just click here on refine anisotropically. So now we have residual densities all over for probable hydrogen atoms, and let's see if we can just automatically add them like this. And as you can see, they look a bit strange for a molecule with double bonds, but there is also this palladium atom which is bond to them, so this is considered then not really CH2 ending of a double bonded species, but we have here another extra bond, so it's will have a different affix. It's just affix 2,3, and here it's 13, and so let's see if the structure will work after refining that. No, not too bad. We see residual densities all over on the bonds, which is a good indicator most of the time. And if we just grow the structure, now we see we have here some ghost atoms because they are on special positions. So, which means yeah, they're extra atoms by symmetry. If you don't like those ghosts, you can click here to hide them, and with that we can highlight those extra parts. Yeah, so principle, so if I put more effort, I probably could move that a little bit so it fits the residual density of that BF4 entity a bit better. Just playing around a bit would help. So let's see our occupancies. They're close enough to 0.5, so we don't really need them. So we have to go here in our part commands. So this 21 here, I just change into 10.5. Oh, German keyboard. This should be a point. And same goes for here. So here we just put that into 10.5. So let's refine that. And now there's something I'm not really a fan of, because we have here our residue M001, then we have BF3, and then again M001. Let's see if we can sort that thing in the file. And yes, it seems to be working. Yeah, so let's refine that again, and Next thing I try is if this thing has some extinction effects, which we have to consider by a simple single value. Slightly, but very small, so it's probably a good idea to omit that and just go on by refining the weighting scheme. So finally we have refined that structure to 2% and 0.12. So that's it for this structure. Thank you for listening.